So, good afternoon to all of you. In our subject selected topics in decision modeling, today we shall continue our previous discussion on integer programming formulation. In the previous lecture, we have seen some of the formulation examples, and let us continue from where we were there in our previous lecture. So, the first formulation problem that we shall consider is the modeling of either or constraints. Sometimes it happens like this, that we have an integer linear programming problem where there are series of constraints, but there are some constraints where either a given constraint has to be satisfied or the other constraint has to be satisfied. So, let us see what is that problem. So, suppose the following two constraints are given, that is 5 x 1 plus x 2 plus 9 x 3 less than equal to 1500 and 2 x 1 plus 3 x 2 plus 4 x 3 less than 1000. The idea here is supposing we have to have only one constraint to be satisfied, either the first one or the second one, then how should we model? That is the question. So, we want to ensure that either constraint 1 or constraint 2 is active, called either or constraints. How to achieve this? Is all right. So, what should be done? Look here, this is where we can cleverly use some binary variables. Now, if we have to have a binary variable, let us say y, then how do I connect y? Please remember that these constraints are all less than equal to type. Is it all right? That means, the 1500, that left hand side should be less than 1500 on the first occasion, and the left hand side should be less than 1000 in the second occasion. Now, how do you ensure that a particular constraint is not required? So, what to do? You add some quantity which is very high. Say, suppose the first constraint, if we can write say 5 x 1 plus x 2 plus 9 x 3 less than equal to 1500 plus m. What is m? M is a very large quantity. So, m is a very large quantity, and if we can write like this, then what will happen? Then this constraint is redundant. Why? Why this constraint will be redundant? Because look at the right hand side, the 1500 plus m, this is a very high quantity because m is very large. So, m plus 1500 will also be very large, and 5 x 1 plus x 2 plus 9 x 3 will be always less than a very large quantity. So, what will happen? This constraint will be null and void and therefore not active. Is it all right? The question is now that we know now how to make a particular constraint non-active, but then how to cleverly really put things in such a manner that m is added sometimes, m is not added sometimes. So, how to do that? How to ensure that m is added sometimes and m is not added sometimes? In fact, if we add m in the first constraint, then we do not add m in the second constraint. Is it all right? Or if we add m in the second constraint, then we do not add m in the first constraint. How to achieve this? Make use of the binary variable and then write the equation in such a manner that let us say 5x1 plus x2 plus 9x3 less than 1500 plus my, where y is 0 or 1. That means y is binary. So, what happens that if y becomes 0, then the equation is active, constraint is active, and if y equal to 1, the constraint is inactive or redundant, right. So, that is how to really put, but then if I put y in 1 and the second one we should not put y, we may put what? Think over, we may put 1 minus y. So, if y equal to 0, 1 minus y will be 1, and if 1 minus y equal to 0, then y will be 1. That way we can have either or constraints. So, that is what we need to do, and let us see that how to achieve this. So, the constraints may be written as 5x1 plus x2 plus 9x3 less than equal to 1500 plus my, 2x1 plus 3x2 plus 4x3 less than equal to 1000 plus m star 1 minus y, and as you have guessed that y is a binary variable. Is it all right? So, that is the way we should model either or constraints. Now, m is definitely a large positive number. Now, please note that y equal to 0 means constraint is active, y equal to 1 means constraint is not active. That means, if y equal to 1, m is added, and 1500 plus m is a very large quantity, and therefore, the constraint is not going to come in. That means that LHS will be always less than this quantity at all times, right. Now, to generalize this, we can now have another type of problem which we may call modeling k out of p constraints. So, total number of constraints say are 10, and let us say we say that 7 of them should hold and others should not hold. Then what should we do? So, let us say again the problem is the f1, x1, x2 to xn less than equal to d1, f2 function of x less than equal to d2, and dot 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 up to fp, which is again function of x1 to xn less than equal to dp. So, how are we going to ensure that out of these p different constraints, k will hold, remaining k will not hold. So, how do we go about this? Only some k of these constraints must hold. How to achieve this? Think over, again we can probably add those variables, but should we add y and 1 minus y? Just imagine for the time being, in the previous problem, suppose we have added y and 1 minus y. Instead, if we added y and z, so what would have happened? We require an additional constraint that y plus z equal to 1. But in this case, if we really think that all these constraints, say the first constraints, supposing we say that f1, x1, x2 dot 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 to xn less than equal to d1 plus my1, all right. So, this is how we can implement by going the similar logic, and in the second case, supposing we put less than equal to d2 plus my2, and the last one will be fp, the second one will be f2, fp x1, x2 to to xn less than equal to dp plus myp. So, all these constraints. So, what can you infer or what is your idea about y1 plus y2 plus y3 plus yp should be equal to how much? Should it be k or something else? Just think over. See, the point is, if yi equal to 0, then constraint is active or non-active. Just think, if yi equal to 0, then constraint is active. So, we want the number of active constraints to be k, and yi equal to 1, that means the constraint is redundant or non-active. So, if the constraint, so you see p constraints, k constraints are active, so how many constraints are inactive? How many constraints are inactive? Please think over. If that means an inactive constraints will be added to 1, is it all right? K constraints are active, that means k of them are 0. So, how many are non-zero? That means inactive constraints, it should be p minus k. So, it is the p minus k which should be the sum, that is all the yi's, when you add, the sum should be p minus k. Is it all right? Because that is the number of inactive constraints and those values should be 1, remaining values should be 0. That means, k constraints having yi value equal to 0, and therefore, those constraints will be active. I hope you got the essential idea. So, let us see how it is that modeling k out of p constraints, the generalizing the big M method as used in either or modeling example, following set of constraints, that is the first one, the function of f less than d1 plus my1, second one less than equal to d2 plus my2, third one like this, the last one dp plus myp, and all these sum of y1, y2 up to yp should be p minus k as we have explained, and also to note all these yi's are binary, right. So, this is how we model either or constraints, or in a generalized way, let us say the k out of p constraints. So, once we know this, let us take an example problem. A company wishes to ship crates of a number of items from place A to place B in a truck. There are 6 types of items. For each item has a weight and has a value. It is like a kind of knapsack problem. The company wishes to maximize total value of consignment. It is known that the truck can carry a maximum weight of 1500 units. Formulate the integer programming problem also including the following constraints. Number 1, not more than 10 crates of a given type of item can be sent, right. Type 3 crates can be sent only when there are at least one type 4 crate. At least 5 crates of type 1 and type 2 can be selected, or at least 5 crates of type 5 and type 6 can be selected. Is it all right? So, how do we go about this? Right. So, first part of the problem is very simple, that is it is a standard knapsack problem. So, we can just formulate this in the form of a knapsack problem formulation, that is maximize the total value which is 50 x 1, 40 x 2 etc., subject to the constraint that this should be within that 1500 limit. That means the total value total weight should be within the 1500 units, right. So, 30 x 1 etc. should be less than equal to 1500 and x size should be greater than equal to 0. We have already seen how to model such problems in the form of a integer programming problem. So, this part is simple, but the additional constraints, let us see how we have modeled. The first constraint, that not more than 10 crates of a given item can be sent. This is very straightforward. That is that for every item xi should be less than equal to 10, right. So, it is very simple, that means x 1 should be less than equal to 10, x 2 should be less than equal to 10 and like that. The second one, look at very carefully, type 3 crates can be sent only when there are at least one type 4 crates. Is it all right? So, it means that if there is a type 3 crate, even one, then there should be at least one type 4 crate. See, what should be the maximum value of x 3? It is 10. So, look here, x 4 can be x 4 should be, if x 4 is 0, then 10 x 4 will be 0 also. But then that will not satisfy this particular constraint. Just imagine for the time being that x 3 equal to 2 and x 4 equal to 0, then this constraint will be violated. But if x 3 equal to any value within up to 10 and x 4 equal to 1, then this, or any number more than 1, this constraint will be satisfied. So, we can write here the constraint is satisfied for x 4 greater than equal to 1, right, but not if x 4 equal to 0. Okay. So, automatically you can understand that there should be at least one type 4 crate, this constraint will be satisfied. Look at the third one, at least 5 crates of type 1 and type 2 or at least 5 crates of type 5 and type 6 can be selected. So, initially let us think of let us take out this part first. Suppose if they do not exist, suppose that part does not exist. So, what would be then, that at least 5 crates of type 1 and type 2, that means x 1 plus x 2 should be greater than equal to 5, and at least 5 crates of type 5 and type 6, it is x 5 plus x 6 greater than equal to 5, right. So, these constraints are satisfied, but then if you satisfy the first one, then it is not required for the second one, or if you satisfy the second one, it is not required for the first one. So, that is where we can bring in our concept of binary variables, that is we multiply it with a binary variable y. If y equal to 0, then the constraint will be always satisfied, is all right. That means you do not really need at least 5. But then if y equal to 0, 1 minus y will be 1, then in the second case must be satisfied, and if y equal to 1, then 1 minus y will be 0. So, the first case should definitely be satisfied, is all right. So, this is the interesting way by which you can model such kind of constraints. Obviously, the y is binary and xi is a value from 1 to 6. So, you have seen how these kind of problems are solved or not really solved, formulated. The formulation part of it you can understand. The solution we shall discuss a little later. Now, let us see now the that is the final formulation. So, let us see what are the different types of integer programming problems that we can have. The integer programming problem, mostly we shall discuss integer linear programming problem. I mean, you should know that the integer programming problem includes obviously non-integer programming problems also, but then for the time being we shall not really discuss about non-integer, non-linear kind of programming problems. We shall mainly discuss the integer linear programming problem, that is ILP. Now, such problems are essentially of three types. One is pure integer programming problem, binary integer programming problem and mixed integer programming problem. The pure integer programming problems where all the xj values are integers. The binary problems are such where the value could be 0 or 1, is all right. And the mixed integer, some of these variables are regular, they need not be integers, whereas the others should be integers, right. So, as you can see, all of these are special class of problems, because while we have very powerful simplex algorithms available for solving linear programming problems, but moment we have integer programming considerations, whether pure or binary or mixed, solution becomes difficult, because we just cannot use the simplex programming solutions and the way we know, right. We may have to either modify or use some other methods. So, let us see some examples. Let us see an example of a pure integer model. So, let us say a machine shop is planning to purchase a new press and a new lathe, is all right. So, the marginal profitability, each press rupees 100 per day and each lathe is rupees 150 per day. We want to buy number of presses and number of lathe, but then our total budget is 40,000 rupees only and we have a 200 square feet floor space, and these are the machine details, the price and the required floor space details. Is it all right? So, how do we model this, right? So, what should we do? We should take then two variables, let us call them x1 and x2. So, let us say press we buy x1 number and lathe x2 number. Is it all right? So, what is the objective function? The objective function is to maximize profitability. So, what it should be? Maximize, say z equal to 100 x1 plus 150 x2. So, this is the objective function. What are some constraints? The constraints will be subject to, first of all, the budget constraints. So, 8,000 x1 plus 4,000 x2 should be less than 40,000 as the budget constraint, and the required floor space constraints 15 x1 plus 30 x2 less than equal to 200, and x1 and x2 are integers. Obviously, they are greater than equal to 0, but they are also integers, because you cannot buy some 0.5 press or 0.5 lathe and all that. Is it all right? So, that is what is essentially are pure integer models, right. So, let us see then the formulation once again. Maximize z equal to rupees 100 x1 plus 150 x2 subject to 8000 x1 plus 4000 x2 less than equal to 40,000, 15 x1 plus 30 x2 less than equal to 200, I mean within the flow space, and x1 and x2 greater than equal to 0 and integer, right. So, this is a pure integer model. The next one, a binary model. So, let us say recreation facilities are to be created and we have a budget and we have the total amount of land, and there are 4 types of recreation facilities are to be created: swimming pool, tennis center, athletic field and gymnasium, right. Each has a cost and expected usage and land requirements. So, here the difference is that unlike the lathe and press, we are not going to really create more than one swimming pool or one tennis center, one athletic field or one gymnasium. Is all right? That means either we create a swimming pool or we do not create. Is all right? So, if that is so, then again assuming 4 variables x1, x2, x3, x4, they all will be binary and they will be subject to the usual objective function and the constraints. So, what are they? Let us see them. The thing will be the maximize z equal to 300 x1 plus 90 x2 plus 400 x3 plus 150 x4. Why? Because these are our expected usage, we want to maximize them, subject to the monetary constraint and the land constraint. Is all right? And x1 plus x2 less than equal to 1, that is an additional constraint that we have given, that is that we should create either swimming pool or tennis center, not both. So, right. So, it is also said that you cannot have both swimming pool and tennis center. So, if that is so, then we have x1 plus x2 less than equal to 1 and all these x1, x2, x3, x4 are 0 or 1. Is it all right? So, I hope you understood about the binary integer modeling problems. The next one is the mixed integer models. Now, suppose I have certain money available for investment providing return for flat land and municipal bonds. Is all right? So, the flat cost is given, and if you sell after 1 year you are going to get a profit of 9,000. The land also has a cost per acre and you will make a profit of 1500 if sold after 1 year, I mean per piece of land. The municipal bond on the other hand costs 8,000 per bond and you have 1,000 profit if sold after 1 year. So, only 4 flats, 15 acres of land and 20 municipal bonds are available. So, how do we go about it? So, again we assume x1, x2, x3 flat purchased, right, then acres of land and bonds. But please remember that while the flat has to be an integer, the bond has to be an integer, there is no such need about the land. You can purchase land need not be in integer, you can buy let us say 2.5 acres land, there is no problem. Is all right? So, that is how it is a mixed integer problem, and obviously if you look at the previous slide, then the the returns are 8000, 1000 for 9000, 1500 and 1000 respectively. So, 9000 x 1 plus 1500 x 2 plus 1000 x 3, that is an objective function to be maximized, subject to the 50,000, 12,000 and 8,000, which are the costs. So, 50,000 x 1, 12,000 x 2 plus 8,000 x 3 should be less than the total amount available. X 1 is less than 4 flats, x 2 is less than equal to 15 acres and x 3 is less than equal to 20 bonds, and they are all greater than equal to 0, but additionally x 1 and x 3 are integers. Right. So, we have seen that how different kinds of integer programming problems are formulated. In our next lecture, we shall see how we can solve such integer programming problems.